The AI boom isn't just about chips, it's about a $700 billion plus capital spending wave, much of it driven by AI infrastructure. In 2026, Microsoft, Amazon, Alphabet, and Meta are on track to spend roughly $700 to $725 billion combined on capital expenditures. Much of that spending is being driven by the race to build AI and cloud infrastructure. Before the generative AI boom, hyperscaler capex was already enormous. What changed wasn't that big tech suddenly discovered data centers. It was the speed, density, and scale of infrastructure AI now requires. The bottleneck keeps expanding. It started with GPUs. Then HBM and packaging joined the constraint. Now power, cooling, and grid access are becoming just as important. It starts with compute. NVIDIA's GPUs, along with custom chips from Google, Amazon, and Meta, do the actual math behind every AI model. But raw compute power is only half the story. At the compute layer, NVIDIA and AMD sell merchant accelerators, while hyperscalers increasingly deploy custom silicon like Google's TPUs and Amazon's Trainium. To put that in perspective, NVIDIA's data center business alone pulled in $75 billion in a single quarter this year, up 92% from a year earlier. A GPU can only calculate as fast as data reaches it. If memory can't keep up, expensive compute sits idle waiting for data. That single problem is why memory became the next battleground. That's how HBM went from a niche memory technology to one of the biggest bottlenecks in AI hardware. In memory, 3 companies dominate HBM production: SK hynix, Micron, and Samsung. HBM supply remains extremely tight. Micron has already contracted its entire 2026 HBM supply, SK hynix is locking in long-term AI memory partnerships, and Samsung is now mass-producing HBM4. HBM delivers its advantage by sitting extremely close to the GPU, connected through a very wide interface. Making that work at scale is an advanced packaging problem. TSMC's advanced packaging technologies integrate GPUs and multiple HBM stacks into the same package. Without that high-bandwidth integration, much of the GPU's compute capability would be wasted waiting on data. In advanced packaging, TSMC sits at the center of the ecosystem, supported by OSATs and a growing network of packaging equipment and materials suppliers. A single AI model now needs thousands, sometimes tens of thousands, of these combined units working together. Connecting them all is its own massive engineering problem. That's where networking and optical interconnects come in. Companies like Broadcom and Arista build the high-speed links that make thousands of GPUs behave like a single giant computer. In networking, it's NVIDIA again, plus Broadcom, Arista, and the optical component makers connecting it all. Broadcom disclosed a $73 billion AI semiconductor backlog scheduled for delivery over 18 months, spanning custom accelerators and networking. All of that hardware, densely packed and running constantly, generates an enormous amount of heat and draws an enormous amount of electricity. That's where the next bottleneck begins. This creates 2 more industries around AI. Companies like Eaton supply the electrical infrastructure, while companies like Vertiv provide power management and increasingly liquid cooling systems. As rack densities rise, conventional air cooling alone becomes harder to use efficiently. In power and cooling, Eaton supplies electrical infrastructure, Vertiv supplies power management and liquid cooling, and utilities supply the electricity itself. Vertiv's backlog reached $15 billion by the end of 2025, more than double its level a year earlier. And this is where the bottleneck starts, leaving the semiconductor industry altogether. Global data center electricity use is projected to more than double, from about 415 terawatt-hours in 2024 to roughly 945 terawatt-hours by 2030, according to the International Energy Agency. Even after the hardware and power systems are ready, someone still has to build the physical site and connect it to the regional power grid, a process that can take years. In site and grid work, it's data center developers, construction firms, and the local utility building out new transmission capacity. And once that infrastructure comes online, the direction of the money reverses. The hyperscalers now have to earn it back through cloud usage, AI services, and software. The bottleneck hasn't moved from one layer to the next. It's expanded to include more of them. Around 2023, compute scarcity emerged. Through 2024 and 2025, HBM and advanced packaging joined the constraint. Heading into 2026 and beyond, power, cooling, and grid access are becoming just as critical. The AI trade isn't disappearing, it's spreading outward. But every supplier's revenue is someone else's capital bill. Here's a real number to watch. Amazon's trailing 12-month free cash flow fell from $25.9 billion to $1.2 billion as property and equipment spending surged, according to the company's own Q1 2026 earnings release. That doesn't mean AI spending is failing. It shows the scale of the financing burden. From here on, every episode in this series comes back to three questions. Where is the bottleneck? Who controls it? And can the companies funding all of this earn their money back? The real question isn't where the $100 gets spent. It's which layer keeps the highest return on it. And one of the strangest winners sits right next to the GPU. HBM. That's episode 2.